In this video, we're going to discuss constrained extrema, that is, maximizing or minimizing a function given a set of constraints. And we're going to do this with method of Lagrange multipliers. So first we'll talk about the Lagrange multiplier and kind of look at that pictorially, what that looks like. And then we'll discuss analytically how to solve the problem. We'll have a number of examples, I think 3 or 4, and then I'll have 2 problems for you to do by way of review. And then our last main topic is about looking at the case of multiple constraints. So as I said, often when we maximize or minimize a function, we are subject to certain constraints. So we have this Lagrange multiplier theorem. If f, that's going to be our function we're maximizing or minimizing, is a function from Rn to R, and g, that's going to be our constraint that goes from Rn to R. They're both smooth functions. We're going to let x naught be an Rn. And then we're also going to say that we're going to look at g of x naught is equal to some level surface, and S is going to be the level surface for g with value of c. Then assume the gradient at g at x naught is not 0. Then we can say f restricted to S. So that's what this f with the line is. And it's very much like the conditional probability, f given S. So f restricted to S has a maximum or minimum on S at x naught. Then there's a real number lambda such that the gradient of f evaluated at x naught is equal to lambda gradient of g naught. So this is the important function here, and just remember f is the function you're trying to minimize or maximize, and g is your constraint. So there's this relation here if there is a max or min. And we also have this corollary. If f, when constrained to a surface S, has a max or min at x naught, then the gradient of f at x naught is perpendicular to S at x naught. So you can kind of imagine if you're at some peak or top of the hill, and you can also imagine the trough, and then you have this level surface at the top of the hill, then your gradient is going to be perpendicular. Well, among other things, it's going to be perpendicular to any level surface. But anyway, we'll continue. We'll use this first example to look at these ideas both graphically here and then on the next screen analytically. So we define a function f is equal to x squared plus minus y squared, and S is going to be a circle of radius 1 around 0, 0, and we want to find the extremes of f on S, or restricted to S. If we recall, f of xy equals x squared minus y squared is a hyperbola, and I do have some level surfaces here, so if we set f of xy equal to 0, we get x is equal to plus or minus y. So this is our level surface for x, these two lines. And then if we set it equal to 1, then we have the hyperbola with the axes at 1 and negative 1, x equals 1 and negative 1. So here's f of 1, here's f of also f of 1. And then if we set f of xy equal to negative 1, that's essentially the same thing, except because on an ellipse, or no, on a hyperbola, we have to have x squared minus y squared, we have to have this term equal to positive 1. We switch, y becomes positive, so that becomes our major axis. So here is the intersection, it intersects on 1 and negative 1. So here's our level curve for f is equal to negative 1. And then we have a bunch of other level curves, which I went ahead and put in green and blue, just other level curves, bigger and smaller. So what we want to look at then, is also how the circle of unit circle around 0, 0 looks compared to our function. And I'm going to apologize for my circle. It looks more like a squashed oval. But anyway, so we have this circle, pretend like it's a circle, of radius 1. And we want to find our function, where our function f is maximized, but we're restricted to this circle. So if we look at this, here I have a level curve where f is less than 1. And you can see it does intersect the circle at these 2 points here. But you can see that we haven't maximized f, because obviously if we go further out here, we can have f is equal to 1. Here f is smaller than 1. So we haven't maximized f as long as we're inside the circle. Also, we have this blue curve here, which is it's a bigger value than this f equals 1 here. This is a larger value. But you can see that we're outside the circle. We're no longer touching the circle. So our maximum value of f is going to be when f just touches the circle, when f is tangent to the circle. And what I just described is what I tried to write down here. First, you consider the blue level surface. Its value is greater than f equals 1, but it's too big to intersect the circle. Then you consider the green tangent line, and it intersects the circle, but so does f. So it intersects the circle at these 2 points, but f equals 1 also intersects the circle, and f of 1 is bigger than this value of f. So to maximize f and still be on the circle, so you can think of, there's all these level curves, different functions where f is equal to different values, but to maximize it and still be on the curve, you want the level surface of f to be tangent to the circle. So the tangent of the circle meets the tangent of f, and that's where this formula comes from. It's the gradient of f meets the tangent of f. And again, the gradient, though, it can be a scalar multiple of this gradient of g. So that's kind of the intuition behind this formula. Next, we'll talk about how to use it analytically. So we're going to look at the gradient of f, so that's going to be 2x minus 2y, and it's going to equal to lambda. It's a scalar multiple of our gradient of g. Oh, so I need to talk about g. G is going to be x squared plus y squared equals 1. So the gradient is going to be 2x and then 2y. So now that these two are equal, I'm going to get the equation 2x is equal to lambda 2x, setting the first coordinates equal. Setting the second coordinates equal, I get minus 2y is equal to lambda 2y. And then I have my function for the circle, because we know we're on the circle, x squared plus y squared is equal to 1. So now we have 3 equations, 3 unknowns. And again, your third equation is always your constraint, because that is something that you want to be true. Looking at my first equation, 2x equals lambda 2x, so I'm going to divide out my 2x, but when I divide by 2x, I'm assuming that x is not equal to 0. So what that will give me is lambda equals 1. And if lambda equals 1, if I plug in lambda equals 1 here, I'm going to get that y is equal to 0. And then when I plug in y is equal to 0 here, I get that x is going to equal to plus or minus 1. So this is my first set of solutions. But I did assume that x was not equal to 0, so I could divide. But it's possible that x is equal to 0. In which case, if x is equal to 0, when I solve this equation, I get lambda is equal to minus 1 and y is equal to plus or minus 1. So our potential extrema are, I have x is equal to plus or minus 1 and y is equal to 0. So that's these two possibilities. And then I have these two where, where's my x value? X is equal to 0 and y is equal to plus or minus 1. So I have 4 potential extrema. And to see if they're minimum or maximum, you do all those things that you learned about in the other video, the last section, which was about finding minimum and maximum and classifying them. So that's really the main ideas. And you will find when you get your 3 equations, 3 unknowns, you often have different cases, like here where we had the case that x was not equal to 0 and x is equal to 0. So I'll do a few more examples for you. We also want to be able to use this technique when we have multiple constraints. So we'll do an example. F of x, y, z is equal to x plus y plus z. And we're subject to 2 constraints. X squared plus y squared equals 1. And x plus z is equal to 1. So we have g1 here and g2 here. So what we have is delta f is equal to lambda 1 g gradient of g1 plus lambda 2 gradient of g2. So what we get is the gradient of f is going to be 1, 1, 1 is equal to lambda 1, 2x, 2y, 0 plus lambda 2, 1, 0, 1. And then we set our equations. So we have an equation for x, we have an equation for y, we have our last equation for z, which is just 1 times this is 0 plus lambda 2 equals lambda 2. And additionally, we have our 2 constraints. So from equations 1 and 3, if we plug in lambda 2 here, we plug in 1 for lambda 2, we're going to get lambda 1, 2x is equal to 0, which means that either x is equal to 0 or lambda 1 is equal to 0. So the first case, if x is equal to 0, then we use equation 5 and we get z is equal to negative 1. And then using equation 4, we get y is equal to plus or minus square root of 2. And then I didn't even really need to solve for lambda. Why do I keep doing that? I don't know. Anyway, if lambda 1 is equal to 0, then if I plug in into equation 2, I get that 1 is equal to lambda 1, which is 0. So I get 1 is equal to 0. So that's a contradiction. So that means that lambda 1 cannot equal to 0. And the only solutions we have are, or actually we have multiple solutions, is when x is equal to 0, y is equal to plus or minus 2. So there's two solutions here. And then z is equal to minus 1. This next example is just about in every textbook you can find, I guess because it looks like something real, like a real application. But anyway, find the largest volume of a rectangular box you can have, subject to the constraint that the surface area be fixed at 10 meters squared. In other words, so your materials is restricted, but you want the largest box. We have our equation for volume, which we are trying to maximize, x, y, z, and then we have our equation for surface area, which is our constraint. And then we have 2xy plus xz plus yz equals 10, and we just kind of divided everything out by 2 to get this equation, just to simplify it a little. Now we use our Lagrange method of constraints. So we take our derivative of f here with respect to x first, that's our yz. With respect to y, we get xz, and with respect to z, we get xy. And then we multiply by lambda times the gradient of g, which we're going to get first with respect to x, that's going to be, oh, I'm going to look over here, is going to be yz. With respect to y, we're going to have xz, and then with respect to z, we're going to have xy. And now we set our components equal to each other with the lambdas, so yz is equal to lambda y plus z, our xz is equal to lambda x plus z, and our xy is equal to lambda x plus y. Okay, oh, and then our last equation we have is our constraint, which I keep pointing over here, but it's simplified to xy plus xz plus y. No. Oh, I think this should be xz equals 5. Okay, so I fixed this last formula here. So now I'm going to have yz over y plus z, that's equal to lambda, which is equal to xz over x plus z. And what we get from this is that x is equal to y. Similarly, we can work with these two, and we get that y is equal to z. And when we plug it into here, a little more algebra will show us that our extrema point is square root of 5 over 3, square root of 5 over 3, square root of 5 over 3. Our next example, we're going to let s, our constraint, be the line through the point negative 1, 0, inclined at a 45-degree angle, and f of xy is equal to x squared plus y squared, the circle of radius 1. And we want to find the extrema of f restricted to s. So I wrote the equation of the line here. Since it's at a 45-degree angle, we know the slope is equal to 1. And then I rewrote that as a level surface, so y minus x minus 1 is equal to 0. Our constraint then is equal to y minus x minus 1, and we have c equals 0. So our gradient of g is equal to minus 1, 1, and our gradient of f, where's f over here, is equal to 2x, 2y. So we get 2x, 2y is equal to lambda minus 1, 1. So from here we get that 2x plus 2y is equal to 0, which gives us x is equal to y. And then looking at y equals x minus 1, we plug in and we get y is equal to 1/2 and x is equal to minus 1/2. And you can look at this graph here and you can see that this line is tangent to the circle, which is what we expected and discussed in our previous slide. We will start by taking the gradient of f and set it equal to lambda gradient of g. So here's my gradient of f, my lambda gradient of g. We set the components equal to each other. 2 is equal to lambda 1/2 x to the minus 1/2, and 1 is equal to lambda 1/2 y to the minus 1/2. And then we put our constraint in at the bottom as our last equation. So we have 3 equations, 3 unknowns. You can see I multiplied the 4 over, and I have lambda over square root of 4. So then multiplying both sides, I get 4 square root of x is equal to lambda. Similarly here, I get 2 square root of y is equal to lambda. So I have square root of y is equal to 2x, the square root of x. I plug that into this equation here, and what I get is that x is equal to 1. And when x is equal to 1, y is equal to 4. So I have this point, f of 1, 4, which is equal to 2. And I have to tell you, normally I would never graph these things unless someone told me to. But if you graph it, you see that this constraint gives you a closed bound area, or domain. And so if you're within this closed bound domain, in the previous chapter, we said that you should be able to get a minimum and a maximum. And here we only have one value, so it can't just be a minimum and a maximum, this one value. But what we do know is also from the previous chapter when we talked about min and max, when you have this closed bound domain, you need to look at the endpoints. So we're going to consider 9, 0 and 0, 9. They satisfy G, and the reason why they don't show up with the Lagrange multiplier is because at that point, the gradient of G is not defined. You can see here's the gradient of G, and here x is in the denominator, so this point is not going to be defined. And here y is in the denominator, so this point won't be defined, which is why it did not show up when we did this Lagrange multiplier method. So we do need to check 9, 0 and 0, 9, and we find that 9, 0 is 18, so that's going to be our maximum. And 0, 9 is 9, so that's neither maximum or minimum because our f1, 4 is our minimum. And I specifically included this example because of this bound closed domain, which I never would have found because I don't graph things unless someone tells me to. But hopefully you can keep that in mind and you'll do better than I. This last example, here we want to find the extrema of f of x is equal to x squared over 4 plus y squared, subject to the constraint that we're on this circle. So first, this x squared over 4 plus y squared, that's an ellipse, and our major axis is 2, so it's kind of twice as wide as it is tall. And then we have our circle, which is in blue, this lovely, I don't know why my circles were off today, but anyway. So we take the gradient of f, and we have it as a multiplier of the gradient of g. And from there, we get these two equations, and then we add our constraints. So we have our 3 equations, 3 unknowns. Looking at the second equation here, there are 2 possibilities. Either lambda is equal to 1 or y is equal to 0. So we'll look at the first possibility here, and then we'll look at the possibility y is equal to 0 here. But we'll start with lambda is equal to 1. If lambda is equal to 1, and I look at this equation over here, it has nothing to do, oh yeah, it does have something to do with lambda. I get 1/2 is equal to 2x, which must mean that x is equal to 0 because, yeah, there's no other value of x that would work. And then when I look at x squared plus y squared equals 1, that'll give me y is equal to plus or minus 1. Next, I need to look at the possibility that y is equal to 0. So if y is equal to 0, I looked at the second equation, but I don't even need it. I can go straight to here. X squared plus 0 is equal to 1 gives us that x is equal to plus or minus 1. And then I have 4 possible extrema. I have x equals 0 and y is plus or minus 1, or I have y is equal to 0 and x is plus or minus 1. You can use different methods from the other chapter to determine the nature of the extrema, but you can also look at these level curves. So again, you're looking to see where the level curves are tangent, and we have the x equals plus or minus 1, or the y is equal to plus or minus 1. You can see here, this level curve has a larger value of x, so at the y equals plus or minus 1, those are the maximum, because here the level curve has a smaller value. And looking at this graph is the easiest way to determine which are the max and which are the min. So that covers most of the material for Lagrange multipliers. We looked at when we want to find the minimum or maximum of f restricted to some graph, some constraint s, we look at the gradient of f, and that's going to be a multiplier of the gradient of our constraint g. We looked at what that meant. Graphically, that means that f is going to touch, we're looking for where the graph of g touches tangentially tangentially a level surface of f. Analytically, we use the formula gradient of f is equal to a scalar multiple of the gradient of g. And then finally, we had looked at how to handle multiple constraints, and that would be gradient of f is equal to lambda 1 times your first gradient of your first constraint plus lambda 2 times gradient of your second constraint, and you can go up to n, so it's lambda n times gradient of the nth constraint. So now, by way of review, I have two problems for you to try. You can pause the video, give them a try, and then I'll have solutions for you on the next slide. So here's the solution for the first problem. Because of the two constraints, this is a little more algebraically involved, so I'll walk you quickly through it without really going through a lot of detail. So I start by taking gradient of f is equal to lambda 1 gradient of g1 plus lambda 2 gradient of g2, which I write out over here. And then I do component by component, so 2x is equal to lambda 1 2x plus lambda 2 times 1. So that's my first equation. I get my second equation by following the y component, and my last equation by following the z component. Then I add my two constraints as my last two equations. So I have my 5 equations, which I have numbered, and I use them. When I use these equations, I put the number of the equation in blue that I'm using. So I start off with equation 1, which is why I have the 1 in blue here, and I group my two x's together, and I have 1 minus lambda 1 is equal to lambda 2. I do something similar with equation 2, and then I combine these two together, and I get 2xy, 1 minus lambda 1 is equal to 0, which tells me either, since it's equal to 0, either x equals y or 1 equals lambda 1. So I work out x equals y, that case over here, and I start with lambda equals 1 over here. Working again with equation 1, I get 2x, plugging in lambda 1 is equal to 2x plus lambda z. So from there I get lambda 2 is equal to 0, and then I use this in equation 3, where I have plug in lambda 2, and I get z is equal to 0, and then I use everything I know about x and y into equation 5, and I get x is equal to negative 1 and y is equal to negative 1. But I see that also x squared plus y squared minus z squared is equal to 0, and these numbers aren't going to give me 0, and so I have a contradiction. I can't solve all. There's no x, y's, and z's that solve all 5, so that means lambda 1 cannot equal to 1, which means that x must equal to y. And then I use equations 4 and 5, plugging in y is equal to x, so I get 2x squared minus z squared equals 0. Similarly, I get 2x minus z is equal to 2. This will tell me that z is equal to 2x plus 2, and then I plug z is equal to 2x plus 2 into this equation here, and I get this quadratic equation. So I solve for it, and I get x is equal to minus 2 plus or minus square root of 2. Plugging in for x, I can solve for z, and then I can solve for y, and these are my two solutions. So that's it for this video. Thank you for watching.